In this particular session, this session is divided into two parts. First part, I will tell you about integrating IoT, fog and cloud infrastructure. And the second part, I will tell you the highlight of iFogSim. Okay. And one of our students is working in the field of iFogSim. He is going to present if possible. Otherwise, we have already recorded the video that will play, that is of another 30 minutes. So you can expect to close this session by 8:30. Then we will conduct the test, which is having 20 MCQs. Each question is having 1 mark. There is no negative mark. So you can appear for that exam. And exam is also compulsory. Okay, because based upon the exam, and your what attendance, you are going to get the certificate. Okay. Everybody is asking about the passing marks and minimum attendance. That is decided by end ICT Academy. Okay, don't worry about it. You attend the session seriously and attend the exam. Right. I hope whatever questions, whatever interaction happens in the last 8 days, the same thing is going to be asked in the examination. Right. And there is a very simple question you have to answer. All the questions are either MCQ type or true false type, so you can answer. Okay, so welcome to this particular session, the last session of this FDP. And in this session, I will tell you about the integration of IoT, fog computing and cloud infrastructure, which is a burning topic, right? So although this integration is not in the mature stage, so if anybody is working as a PhD scholar or any faculty member want to assign the work to in the field of IoT, fog and cloud, you can give this integration part, right? So I have taken this material from one of the book by Professor Kumar, edited by Professor Kumar. That book I have taken, this is a specific chapter, how they have collected the data about IoT, fog and cloud, and how they have searched the paper, what is the search query they have put in the Google or various websites to get the paper. That also I will tell you, so that who are those people who are in the beginning of their research career also, they can use this particular search query. So this search query you can apply in any domain, right? Any particular domain, not necessarily in this particular domain, right? So basically, I was going to tell about why this integration is required and where we are having problems, right, with this integration. That part I will tell you. Then what are the methodologies applied for this integration, we are going to see. Then we are going to see the literature with respect to various years, especially due to time constraint. I will restrict to the modeling techniques in various areas. At least I will tell you the highlight, so that if later point of time, if you are interested, then you can go for, like I will tell you about integer linear programming or mixed integer linear programming, the very famous NAFSA problem, or our Markov model, some distributions, whatever we are using. Based upon that, few people have designed some models. Based upon that, I will discuss a few research papers. Then I will tell you about some of the future research directions where people are working in the now in the current scenario, right, in the area of IoT, fog and cloud. Then I will introduce the iFogSim. Then I have said the link to you, that iFogSim simulator. You can download from internet also. And I will give a very small illustration. You can explore that thing later, right? And I will also show what are the works done by our students in the department. That also in the form of a small video. Okay, so you know that the way the society is changing, it depends upon our technology. Whether the technology may be with respect to the social media, like our Facebook or Twitter, or you are talking about cloud computing today, or fog computing, or you go for IoT devices, or big data, or you go for big data analytics, where we are dealing with various types of data, that may be structured data, unstructured data, or semi-structured data, or the way the mobile technologies are changing. So in this, by using this technology, we are changing our society, and we are interacting with various technology, and we are dependent on the technology, right? Today, the way we are progressing, maybe after 10 years, if some manual work is assigned to a particular person, the person may not do that particular work because there are many automatic things out there, right? So it emerges one new concept that is called as Internet of Everything. Yesterday lecture also somebody asked what is the difference between Internet of Things and Internet of Everything. So I have highlighted in my slide. IoT, we are dealing with interconnectivity of various objects. Objects may be our sensor, maybe our camera, maybe our smartphone, maybe anything, right? But IoE, which is the third information technology platform in which we are focusing on how we can interconnect to various technologies or various processes and peoples into a common platform. Like here we are talking about how IoT devices, fog devices and cloud data centers all need to be integrated so that the latency can be reduced, the memory can be reduced and bandwidth can be reduced. So these are the constraints, whatever there with respect to the IoT environment can be satisfied by the newly developed technologies. So here you can see that there are a lot of applications are there in IoT. They are categorized into various parts. One of the categorizations says that first one is called as large scale distributed control system. You know, there are three layers as mentioned by Professor Jana, that one layer we have IoT devices, the bottom layer we have IoT devices, and these IoT devices are monitored by the fog devices, and fog devices is having limited processing, okay, limited memory. If it is not possible, then you are dependent on cloud, which is having more computational power, more storage, more availability, right? So there are many devices, there are many fog devices are connected to the IoT devices, or you can say group of IoT devices are connected to a single fog devices, another group of devices are connected to another fog devices. Let it be a gateway, let it be a router, let it be anything where whatever the devices available in the fog, right? So there one challenge happened that is called as a large scale distributed control system. The way we are increasing the devices in IoT, definitely we call it a large scale, not in a medium scale and small scale. So how to control these devices through the fog devices, that is very much important. Next, all the applications are deployed from various places. It is hosted in the data center, or now we are talking about the fog devices. It is hosted through the fog devices, right? That is also one of the application area. Similarly, other application area is time dependent mobile applications. So I will tell you there are some applications are there which need the processing within a fraction of time. Like we are wearing the smart watch, right? We need the processing within, for example, smart watch is sensing our heart rate. So within a fraction of second, I want to know what is my heart rate. But if the same thing will be provided after 24 hours, that is of no meaning, right? So there are many applications are there which is relying on the time. Latency is very much important. Delay is very much important. You have to see how you can reduce this thing. Similarly, many applications are there like mobile application. Apart from mobile application, some other applications are also there which is having low and predictable latency. How we can predict also how much latency it will be there if I host a particular application in the cloud. Similarly, I told you about the vendor lock-in problem that is due to the interoperability between the service provider. Today, you are purchasing the thing from X shopping mall. Tomorrow, you are going to Y shopping mall. But in the cloud case, it is very difficult. Today, you have selected X cloud. Tomorrow, you want to move to Y cloud. Then definitely, you are going to face the vendor lock-in problem. So these are the replication areas where we need cloud for storage, maybe for the processing, okay, without compromising on various constraints, like our constraint is memory is a constraint, energy is a constraint, bandwidth is a constraint, or latency is a constraint, right? So existing cloud infrastructure is not well equipped to manage a hyperscale. Okay, so the way we are adding the devices in the IoT layer is not sufficient to manage by the cloud because the latency is drastically increasing, right? So what is the solution? you have to go for a intermediate layer that is called as fog computing, right? Apart from that, what you need various requirements that are required for our IoT devices. Let it be scalability or interoperability, flexibility, reliability, efficiency, availability, security, or the connections between the IoT devices to the cloud in terms of computation or storage or communication. So these restrictions or these constraints you need to fulfill. You can increase the number of devices connected to the cloud. Maybe it is increased to a very large scale, or you can move from one provider to another provider. So such type of flexibility, the restrictions should be provided. Okay, the restrictions should be avoided in the case of when you go for IoT application in the cloud, right? So we need a fog computing layer, as you can see here. So in order to meet the quality of service requirement also, there are a lot of quality of service requirements are there with respect to the devices. And these devices are heterogeneous in nature. Their capabilities and their requirement is different from each other. So everything you have to build in this particular uh, intermediate layer, that is our fog computing, right? So a typical picture where you can see how edge computing, fog computing, and cloud computing are related. Generally, our IoT devices are present in the edge computing layer, right? And cloud is present in the top layer. In between, we have an intermediate layer that is called the fog computing layer. So fog is not a replacement of cloud, but fog is a complementary to the cloud, right? It is not a replacement. Note that after invention of fog computing, many people are thinking it is going to replace cloud. No, it is not possible. Why it is not possible? You can see here because its latency is very low, right? But in the cloud case, you are going to get high latency. In that manner, people are saying, obviously, fog computing is better than the cloud computing. But when the question is asking about high performance, the high performance cannot be provided by fog computing. Or when you can say that support for mobility, right? Cloud cannot provide that mobility, but fog can provide the mobility, right? But high computation, high throughput, high performance cannot be achieved in this particular layer. So still you require cloud computing. Like you can see here, unlimited storage and processing that is not available in the fog computing. High performance is not available in the fog computing. High availability is also not available in the fog computing. That's why cloud is not replaced by the fog. Fog is a complementary to the cloud. So you can see in this diagram, let it be a we are monitoring some smart home, or we are monitoring the traffic control. We are connecting a healthcare like hospital. So all the data are stored in the cloud. How they are stored? Through 10 intermediate devices, right? Like here you can say in the intermediate position, you have some devices, right? So in the bottom layer, let it be a traffic light where I am collecting the noise. I have deployed the noise sensor. I have collected the information about a particular location, and that is given to a fog devices, and that fog devices has to process something and finally store in the cloud. Or let it be a healthcare application. There is a fog device which is processing something and can store that thing in the cloud. Just like if I'll tell you what is the average mark of a particular subject, then you will say that it is a total number of total marks of each and every student divided by the number of students. So that calculation, the intermediate calculation can be done through these fog devices. So such computation, small computation can be done. So the burden on the cloud computing can be avoided. So for this, what happened? So there is a extensive survey that is called a systematic survey. If you are looking for systematic survey, so nowadays people are writing a review paper without knowing their context, right? So if you are planning for systematic survey, so you have to follow this particular process, which is used to here especially we have used these means these particular process, right? To search the paper in the respective directories. Like you have seen here that in order to carry out this integration process of cloud, fog, and IoT, people have searched in three repositories, that is Science Direct and IEEE Explore and ACM Digital Library. Okay, and they have limited their modeling towards two technologies only. cloud computing and IoT, because they know that when the integration is required, then definitely fog will come into picture. That's why they have not included the fog stream while they are searching for the papers. So while they have started searching these papers, they found 1857 papers in a range of 2013 to 2017. It is conducted 3 years back, right? But these 1857 papers are not based upon the analytical modeling, right? So you have to scrutinize these papers to find the papers that are directly dealing with the integration of IoT, fog and cloud. So finally, they got 23 articles, and the articles are excluded because they are not concerned with the integration of cloud to things, or they are concerned with the business modeling, not the analytical modeling. Sometimes what happens, they are focusing on the architecture, not towards the model, which is our reality. So that's why a few papers are excluded, and finally 23 papers are collected in the range of 2013 to 17. So I'm going to tell what are the problems they have solved for the integration in a brief. Okay. So this is the final one, how 1857 paper are collected and how it is scaled to 23, right? So this is the process they followed. If you are planning for a systematic survey in any domain, you can follow this one. First step is you have to identify the need of the review. Why the review is required? What is your objective, right? And whether any review is available or not. Then you have to follow the review protocol. That is nothing but defining the research questions, defining the research string. Like here we have used the string as cloud as well as the IoT without giving the research string as fog. Then you have to choose the databases like IEEE Explorer is there, or Science Direct is there, or SpinDerLink, and lot of databases are there you have to use. And you have to define the criteria that which paper you are going to include it and which paper you are going to exclude it, right? So after doing this review planning process, you have to go for this conducting process, in which you have to identify the primary studies, like you have to read the abstract. If the abstract is not about the cloud IoT integration, simply you have to reject it, right? And you have to evaluate your quality of studies. Like here you can see there is a large number of papers that selected, but they can scrutinize to only a very small number of papers, right? And extract the relevant information based upon the detailed study. Okay, after that also you can exclude, after doing the secondary studies, right? You can exclude some paper. Finally, present an overview of the study and present the relevance of the research questions. With respect to the research questions, what we have framed in the step 2, you have to see that which paper belongs to addressing which particular research question. Like I will ask you whether cloud to IoT integration is required or not, right? What are the protocols are required for this particular conversion, right? Or particular mapping between one layer to another layer. Such type of research questions you can frame, and you have to see which paper fits in that area, right? Now you can see these are the couple of papers. You please go through it. I'll only give you this paper title, right? How they are giving in 2013. There are 2 papers are only there. 2014, 2 papers are there. They are dealing with various technology that I am going to tell you in the upcoming slides, right? Just to show you that I have listed the paper titles from 2013 to 2017, right? Now, if you see these papers, you will find the integration is done through various technology, right? One popular technology they have used, which you may have studied in software engineering, that is nothing but Patrinet, right? The 2 papers are addressing the modeling of cloud to fog to that thing, right? That is called as C2F2T, cloud to fog to your Internet of Things. That is written as IoT devices are represented as T, right? So 2 people have solved using the Patrinet. One person has solved using the Markov chain model. Another people, couple of people are using the integer linear programming and mixed linear programming to perform the integration. Few people have used fuzzy logic, and they have addressed various faults based upon that technique. Few people did with the Bayesian model, that is the conditional probability they are saying. If this thing will happen, what is going to happen? Like I will tell you. Now today temperature is this one. Humidity is this one. What is the chances of rain? Such type of concept they have used for the integration. And many people have addressed the analytical model, where they are focusing on energy consumption, how the gateway is collecting the data, when the gateway will send the data to higher layer, or when the gateway is going to process everything it will monitor in this analytical model. So a couple of papers they found in the analytical model, but people have focused these technologies to perform the integration. Like you can see here, first paper focuses on the architecture, okay, and analytical model is focusing on predicting what is the computing resource requirement. Whatever the IoT devices they are generating the data, whether we have sufficient resources to compute that particular thing or not. That you have to decide based upon the past workload, based on the how the data is increasing. Based upon that, you can model these analytical things, right? So you can see here, many people have focused in the architecture. In our architecture, if you see in the customer end, everything is a virtual infrastructure. But when you looking into, let's say, cloud service provider point of view, everything is physical structure, right? So both physical components as well as the virtual components are represented in the form of vector, right? They have modeled everything in the form of vector, and they have designed a couple of equations for the power consumption and time latency in between these integration, right? And many people also focused on the gateway. So they decided once the data is collected, it will be sent to the fog devices. Whatever data is generated by the IoT devices, it will send to the gateway, right? If it will be sent to the gateway is going to decide whether it can process the data or it should send the data to the cloud for its efficient processing, right? So that decision the gateway is going to do. And for a particular environment, how many gateways are required? The number of gateways that you have to decide, right? And you have to also specify what is the space available in the gateway. And once you are close to this particular space, the data needs to be sent to the higher layer. Otherwise, the new data cannot be received by a fog device like gateway. Few people are also focusing on the scheduling domain, in which they have implemented the processing load of each and every devices, how much memory is free, how much memory is occupied, and what is the bandwidth. Based upon that, they have modeled this thing, analytical modeling, through a set of variables. Many people also focuses on the prediction of the quality of service. For example, you will say the service should be available for 99% of the time. Then by observing the real scenario, you have to decide whether that is achieved or not, right? So based upon that also they can solve various QoS parameters. Not only that, they have also focused on the latency, response time. When a request is made, like Professor Jana told you about the task offloading. Task offloading case, you are giving the data, right, to the nodes and for its processing. So once you are getting the result, the complete transition, we are going to say is task offloading, right? So here we are calculating the response time as a quality of service parameter, right? Now you can see they have defined this thing in the form of an equation. I am not going to tell this equation because you may not understand, but I will tell you what they have focused. They have focused on the CPU utilization. Each and every device is having a processor, right? What is the utilization of that processor? And what is the memory capacity of that particular device, and input bandwidth and output bandwidth. Okay. So based upon that, they have decided which device is going to solve your scheduling problem, right? So whatever work, maybe some work is also done by your IoT devices, because IoT device is also having a processor. So if some work is done, that is your actual working status, if some work is done by the IoT devices, that need to be subtracted, and the rest work will be done by other fog nodes or the cloud, right? In this way, they have designed the scheduling model. Similarly, they have considered various couple of factors. One is called CPU overloading factor. Like you know that each and every devices is having limited capacity, right? Limited storage and limited processing power. So everywhere there is a overloading factor, right? Once you reach to the overloading factor, that device will not going to receive until unless the threshold is reduced. That's why here they maintain CPU overloading factor, memory overloading factor, input bandwidth overloading factor, and output bandwidth overloading factor. Like in mobile network also, you know, for example, a particular network can be provide service to 1000 users. Suppose in that area, more number of users will be there, then it is difficult, right? You may get congestion. So based upon that, they have designed. Similarly, many people have focused on the energy consumption as well as the cloud billing method. So they have calculated what is the consumption rate. They have also focused on the ideal energy consumption. Like I told you in the while we are discussing cloud computing, I told you whenever your devices are active, they are also drawing power. That is called as your ideal power. So they have considered these ideal powers. Okay, based upon that, they are calculating energy consumption of each and every devices, and they have used here the probability density function to do that things, right? Similarly, in the cloud billing method also, they have used two types of billing. One is when the devices is of not used, that is called as your ideal billing cost. It is the first part. Second part is when the device is active, that is your active billing cost. Both costs they have calculated, and they have merged this cost to calculate the final billing. So based upon that also, they can decide that what is the cost that devices need to pay if it is using the services of cloud to fog to the device architecture, right, or such integration. Now you can know that in order to calculate the energy consumption, here there is another formula. You can see we want to connect, for example, we have IoT devices that need to connect with the cloud. So what is the energy consumption by these IoT devices and cloud? That is nothing but, for example, you can see in the bottom layer, there is IoT devices there. In the intermediate layer, you have a fog device. In the top layer, you have cloud data center, right? So in the fog layer, here we have used a gateway, right? So what I can say, a gateway can receive the data from the IoT device and can send the data to cloud, right? And can collect the result from the cloud and send the result to IoT device, right? If it is solved in cloud. Otherwise, this part will be, if the part will be solved in the fog, then only this processing you have to calculate. That's why you can see the gateway receiving, right? Energy consumed by IoT gateway, you have to calculate when receiving the data from IoT devices. Energy consumed by the IoT gateway to transmit the data. Once you are receiving the data, you have to process it and transmit. So based upon that also you need to calculate. And in order to transport the thing from IoT gateway to the cloud, that also you have to calculate the energy, and you have to calculate the processing, the energy consumed by the data center in order to process the work of the IoT devices. So if you calculate these four factors, you can say that is the energy consumed from IoT to the cloud. Similarly, you can take energy consumed from IoT to fog, that is nothing but your receiving energy as well as transmitting energy, and energy consumed through the transport network, energy consumed by DC. But here we have calculated two things. One is a beta factor is added. Beta is nothing but a ratio of the number of updates from the fog to the cloud. Because many times synchronization plays an important role. Repeatedly you are asking how much the task is completed. Okay, and how much is yet to complete, right? For that we have multiplied the beta factor, and energy consumed by gateway to the gateway for local computation and processing is called as your EGWC. So if you merge it, then you can calculate the energy consumption between the IoT and your fog devices, right? Okay, so many people also focuses on the reliability. You have to see that how these devices are connected. If they are connected serially, then you can calculate the reliability in this manner. So they have applied this reliability in the smart home context, right? Where they have calculated the reliability of each and every system. Reliability of the first system, reliability of the second system, reliability of the third system, right? So based upon that, first factor they have calculated. Second, when you are seeking for a particular file, so availability of the particular input file, that also they have considered. Similarly, availability of the K programs running on the virtual machines in the data center, that also they have calculated. Based upon that, they are estimating the total reliability in this integration, and they have applied in the smart home context. Now, many people have applied the NUPSA problem. You know that in the NUPSA problem, you have NUPSA and you are putting so much elements such that the maximum cost you can achieve, right? So before that, there is a question by Odisha that is, how does this formula work for energy efficiency of fog computing in healthcare application? Sir, I told you one particular scenario that if you see in this case, like here we are what we are doing, we are sending the hospital data to the cloud, right? So there you can calculate energy consumed from the devices. Let's say some sensors you have deployed in the hospital. Let it be a you are monitoring the health of a particular patient. That data you are sending to the gateway, and gateway is convert processing it to the cloud. So in this context, we are calculating the energy consumption. Okay, so now you can see here your people have also applied the NAPSA problem. In NAPSA problem, you have a NAPSA and you are putting various items so that the maximum things you can achieve. But here what happened, it is a multi-objective problem where you are focusing how the energy will be, energy consumption can be reduced and how the overall load is reduced and the overall allocation of the services to the infrastructure is also reduced, right? You have to balance the load between the fog and the cloud. You cannot say that all the things I will migrate to the cloud. If you do so, then latency will increase, right? If you solve all the problem in fog, it is also not possible because fog is having the limited capacity and processing power. In this manner, they have done. People have also applied the PutriNet model. You know that PutriNet is used to evaluate two things. One is the performance of a system and it is the dependability of a one system with another system. So I'm directly going to that figure. So we'll discuss more about that. So if you are not comfortable in PutriNet, you can go through this slide so that you will know that how the symbols, what is the meaning of each and every symbol. Like flowchart, we are using different symbols. In PutriNet, we are using various symbols. So you can refer this particular slide. So here they are using four different states. One is your availability, another is called not availability. Availability is represented by AV, not availability is represented by NIV. That is, a node is not available. Similarly, position is represented as in, another is out. Right? We are considering a node or we are not considering a particular node. So they have applied to the mobile crowd sensing framework, especially in the healthcare sector, they have applied. So what is the model? You can see the model like this, okay? So you can see here, this particular node, okay, is called as your process, right? If you go in more detail, I'll tell you, just a minute. So this P is called as your process. Where is that? Written somewhere? Yes. Okay, this P is nothing but process. If it is darkened, then that particular process is having the token. Okay, and T is a particular state. So T will fire if the token is with a particular state. So in that case, in this manner, you can represent a particular method. So you can see here there is a token that will be enabled to start this process, right? That is subscription. So once you reach to this particular state, you have four options, right? One is, I told you, the four states are there. One is AB, another is NAB, that is mode is not available or available, or a device is in or out, right? So based upon that, there are four states are there. So one state is called as your PAB out, right? If you take this one, PAB out, another is, you can see here, PAV in, another is PNAV in, another is PNAV out. So you have four different states, right? So once you reach into their state, you can see that a single state is now connected to four different states. So if you see this particular symbol, the idea will be more clear. This is called as a conflict. So you have to go to one of the state out of these four states, right? So once you go to this particular state, suppose you want to exit from the system, right? Here you have decided to exit from the system. So exit means you have to exit the availability of the system. So you are going to reach that particular device is exited. So your status will be changed from PAV into PAV out because that thing you have exited, right? Similarly, if you want to enter a particular thing, again PAV out is change its mode to PAV in. Similarly, here you can see PNAV in. If you exit, then it will go as a PNAV out. Okay, when you enter a thing, then you can go for PNAV. Because with respect to the scenario, a fog devices may be included, a fog devices may be excluded. right? So based upon that, they have represented in the quadrant. Okay, they have also done this one with respect to, to map the thing in a hospital scenario. They have considered three entities. One is a human user, another there is a personal server which is there in the fog layer, and there is a medical server that is there in the cloud layer, right? So what they did, you can see here, your device is there. Okay, all the devices, the human users are human. For example, a patient's health I am monitoring, so I am collecting through these IoT devices, right? So once I am collecting through these IoT devices, so I will process them into this particular server, right? That is personal server. These personal servers are available in your fog layer. Okay. When you require high computation, you can go for the hospital server, which is there in the cloud, right? So this process they have adapted to perform the integration. Okay, I am telling the highlight only, so you can go through the paper if you are interested in this particular domain, as you have limited time. Similarly, many people have represented in the form of integer linear programming. Whenever the objective functions, you can represent objective function in a linear way or non-linear way, right? So they are modeled in the linear functions. They put several constraints. Based upon that, they are solving. The constraint may be with respect to cost, with respect to energy consumption, with respect to bandwidth, or with respect to the latency. So they have calculated the cost, like in order to calculate the total cost, they are saying you have to calculate the processing cost, storage cost, upstream cost and downstream cost, and what is the link capacity cost. If you calculate all the costs, then they are calculating total cost in order to say it is the financial cost for a cloud to grid architecture, fog to the cloud architecture, which is connected to a metropolitan area network. Right? This is another domain they have used. Many people also applied the mixed integer linear programming, in which they have processed, they have focused on two different areas. One is traffic induced, another is processing induced. Processing induced means whatever work you are doing in a particular device, and whenever you are sending your data from one device to another device or one layer to another layer, traffic induced is coming into the picture, right? So this particular domain also they have explained. Many people also used the Markov chain model to know that we are representing a sequence of random variable in the Markov chain model. Here they have focused on the energy consumption, right? So they have used the gateways in the fog layer in order to collect the information from IoT, okay? And they have calculated the likelihood of a particular event with respect to some given input. Like I am saying, P probability of X such that Y. So some event is given to you, Y event is not given to you. So based upon that, you have to do prediction. So they have used the Bayesian probability, in which we are calculating the conditional probability to solve the particular problem. There is a question by Dr. Hemra that the process I will change in the particular with respect to condition. Yes, you can change. Like they have implemented in the medical domain, right? You can go for any other domains also. So they are focused in three different layers. One is your IoT layer, fog layer, and your cloud layer. Your fog layer, they are placing their personal server, and cloud layer, they are processing, they are giving the hospital server, which they have purchased, which they have they have adapted from the cloud, right? Or they have subscribed from the cloud, right? You can also generalize to your own domain. Okay, so here you can see in the Markov chain model, they have taken four different states. One is the network connection. Okay, another is there is a accelerometer is there, right? And there is a ideal state, and there is a key alive state. Okay, so each and every functionality depends upon this four state. Sometimes there is a transition from this accelerometer state to the network connection state. So the power consumed between these two is called as PAN. Similarly, the power consumption between NC and KA is called as P of KN, right? And in between this ideal and KA, it is PIK or PKI, right? So they have calculated all types of power consumption. So based upon that, they have designed an energy model. And many people also merged two areas. One is fault diagnosis, and another is your fuzzy logic, right? So they have mixed these two areas. That is called as your fault fuzzy ontology. So based upon that, they are focusing various types of faults occurred in the environment, right? So they are focused in the application domain, as well as the devices, as well as the communication between the devices they also consider. So here you can see they focused in the wireless sensor network architecture, where the sensor nodes are there in the bottom layer, which is sensing the environments and collecting the data and send to the gateway. And gateway is onward processing, sending that to the cloud if necessary, right? So these are the faults happen in the fault diagnosis. You can go through it. One is called erratic, another is bias, another is stop, another is hard over, another is spike. Like in a electronics domain, those who are belongs to electronics domain, you know there are two different type of faults are there. One is stockade A 0 problem, stockade 1 problem, right? So such type of faults, if it is there, it is able to identify. As they have represented everything in the form of fuzzy logic, so their decision is not binary, that is 0 or 1. They have taken different steps like low or high, or very low, very high, low, medium, low, something like that. They have moved, right? So this is about the integration part, and a lot of future research directions are there, like management complexity is highly increased if you are adding a new layer, right? As you are adding a new layer, that is fog layer, obviously it will increase, right? But you are going to get the flexibility and resilience, right? But these two things you have to compensate. How you can manage the complexity and how you can provide better flexibility and resilience, right? Many people are focused on the fault aspect. There is a question by Rohit sir before that. Okay, is there offloading problem occur in the Markov chain? Markov chain model, I told you about the energy consumption, sir. Here the offloading is uncertainty. No, they are not doing the offloading work, right? They are not doing any offloading work here. They have modeled through the random variables and they are calculating the energy consumed by each and every devices, right? Or each and every states. Similarly, there are several failures are there. Hawk node may fail, or the server may be fail, or IoT devices while it is transferring the data, it may fail. Okay, so such type of failures also is not well addressed in the literature, right? And obviously, this integration will remain challenging for the next 5 to 10 years, right? So you can focus on this. And those who are interested in the scheduling domain, you can take scheduling problem in the gateway, right? Because the number of requests are received by the gateway, then the gateway is going to decide that whether it is going to solve the request or it is going to going to execute that request by the help of other gateways. So their scheduling problems also comes into the picture, right? Similarly, there is many high criticality applications are there, like especially in the healthcare. So the downtime is still not satisfactory. So we have to work in that domain in order to minimize the downtime and in order to prevent the failure. In any case, if there is a failure happen, then there is a backup node should be available. And resource management is also one of the problem, as we are dealing with heterogeneity. So standardization also plays a very important role. So these are the areas people are focusing. You can focus it. And as I told you about two special problems, one is Markov chain model, another is quadrant model. So you have seen there are several states are there, right? So if you increase the states, imagine you are dealing with a complex problem, right? So you are dealing with several states. So if you are doing that, you are going to face the state space exclusion problem, okay? Because I cannot represent 1,000 and 2,000 states and do the analysis. So in analytical modeling case, it is not possible. So that also you can focus. Okay, before we'll start the iFogSim demo, okay, let me tell you the iFogSim architecture. You can see here there is a 7-tier architecture is there, starting from IoT sensors or actuator is there in the bottom layer. So there is a graphical user interface is there in the FogSim, which I have shared with you. If you have extracted that file, it is a Java project. So you can add a sensors and actuator into a particular environment. Okay. Then above that, we have various fog devices are there. Let it be a router, or it may be a gateway, or it may be some processing power, or it may be some computation power that is there in the fog devices. And some couple of units are there to monitor your work, whether a node is working or not, or whether there is some prediction about the computational requirement or not, or whether there is any failure in the environment is there. That for that a couple of parameters are there, and everything is monitored to an IoT application in the top layer, right? So in the bottommost layer, you have IoT devices, let it be a sensor or smart reader or camera or microphone or collector. Anything can be there in the bottom layer. It is sensing the environment and it is sending that to the upper layer. That is your gateway. So next is it will collect the data, it will send to your gateway. So that gateway can do some processing. If it is not possible, it will send to the upper layers, right? And but iFogSim does not deal with the low-level network issues. So it has a lot of restrictions. Like here you can see there is a low-level network issues is not provided, but a user can model with the high-level attributes like latency and bandwidth. You can model through this iFogSim. Similarly, if you go for the next architecture, if you go for fog devices is collecting the data from the sensor and they are doing the processing, right? And there is a problem with iFogSim. In iFogSim, you can see that many things are not possible. Like if you move from the north to south direction, like this direction, north to south direction, in the case of topology, right, or south to north direction, you can add various devices. But whenever you are moving from horizontal direction, this such type of facility is not available in the current version of iFogSim. Means if a gateway is there, another gateway is there, they cannot exchange their load in the iFogSim, current version of iFogSim. However, a device can be connected to iFogSim can be connected to the cloud, right? Like I told you here, the smartphone to smartphone, IoT device cannot connect with another IoT device, or a gateway cannot connect with another gateway. So that is not possible in the current architecture. Next, in the tier 2, you are getting a sequence of values that they are representing in the form of tuple. In iFogSim, we are calling tuple. It may be your downstream, it may be upstream, it may be related to your bandwidth. These things will be there. So in tier 3, you have the actuators. Various actuators are there. They are monitored. Tier 3 is going to monitor the actuator, sensor, and various fog devices. If they are properly utilized or not, or the connection between these devices, if there is some issue, that will be reported by this infrastructure monitoring layer. The next top layer is called as a resource management layer. Resource management layer is focusing on the quality of service constraints. Okay, whether QAC is satisfied or not, that will be focused, and it will also see that how the resource wastage can be minimized. So here they can implement the distributed approach, or you can implement the centralized approach. But if you go for the current version of iFogSim, so here the static application placement policy is available. There is no dynamic policy available in the iFogSim. Maybe in the upcoming versions, they are going to provide such facilities. Similarly, in the tier 5, they have designed some distributed data flow model. I have shared one research paper with you also, in which 2 scenarios are there with respect to the distributed data flow model. You can go through it, right? And in this model, what happened? The output of a model is provided to input to another module, right? Such type of data generation and data exchange and dependency between the module will be taken by tier 5. And the top tier is your IoT applications, where you can monitor everything to a particular application, or as a user you can monitor the things, right? Okay, so the architecture focus on 2 things. I am going to tell you the first architecture in the demo. One is sense, process, actuate. We have to sense the data, we have to process the data, accordingly we have to act on that particular environment. Actuate means effector, right? Like I have seen in the agriculture field, agriculture land, I have calculated by the help of soil moisture sensor, I have collected the data, right? And I have processed the data. I found that water is required. Then I will tell the motor to supply the water, right? That is your actuator model. Another model is also available in the iFogSim architecture, which is coming under the sense process actuate model, where what happened, a network of application modules running on the fog devices continuously process the data stream. A continuous data stream is collected through the sensor, and accordingly it is processing, right? But in the first case, the static thing is done, right? So this experiment, I will tell you, if time permit, let us see that particular video. Then I will tell you how to create such topology using iFogSim, and how the interaction between these IoT layer and fog layer as well as your cloud layer will happen. That we are going to see with this architecture. So these are the references.